Like what is our line of narration where we are in the course?
Talked a little about Chronicle.
Chronicle, okay. And what is the goal? What was the goal of our discussion last time? The Chronicle seems like technical detail, and Kristen did summarize what we did last time in her presentation. You summarized actually the whole 7 lectures in one slide. Yes, 3 ways to predict future. And we were last time we were dealing with which one? Schrödinger, based on like expansion over eigenstates. So this one is easy. That I hope to collect on Friday. This one is a little harder, but if you are taking differential equations, it will be also math. But often differential equation courses start with Fourier transform. If you are aware of this concept, it will be like 10-15 minutes. If you're not, you look online and get it in like half an hour. But it's not complicated. I promise. Like if you can take integral of sine and cosine, then you can do this homework. And let's chat tonight during the lab. We'll do split time between computer and discussing homework. So, Kristen did it better than I. So we predict future. This is the future. This is the past. We expanded over eigenstates of the Schrödinger equation for given Hamiltonian. And this expansion coefficients enter the expansion with I time-dependent eigenfunctions and time-dependent phase accumulation. Right? Should we assign the highest possible grades to everyone and depart to Christmas? Would be good, right? And would be easier for you. In some sense, you're done with all basic principles. There will be a few more cherries and icings on the cake, but it's major principle. And now, broadly speaking, we left only with applications. So where are we going to apply? Sure, you are. Most of you are chemists. You are chemistry, biochemistry department, and you are thinking about molecules, reactions, maybe eigenstates of quantum dots, maybe some enzymes, right? But those are cool, but a little complicated. I have no doubts in your intellectual strengths and potential. You have all seeds and roots. But before we go to realistic problems, we need to pump mathematical muscles and try to apply our skills to simplest possible guinea pigs. Okay? So we are going to practice this prescription for something that is simplest possible on the point of view of one of us. I do not know if. Okay, there is no time to tune the camera. Maybe it will be focused on the. Maybe there will be on the slides. So, yeah. What is shown on banknotes typically? Portraits. Portraits of who? Of some people who did importance for the country in a political sense. In some countries, people who did something important in cultural sense, and in some countries, people put portraits of those who did contribution in mathematical sense. So I know that when you were in freshman years, there were like classes of 300 people, and grading was a stress both for participants of the class and for instructors, because it's not possible. And there was a procedure of grading on distribution, right? So which distribution is used for grading? Yes. So who designed Gaussian distribution? Gauss, right? So here is the distribution, if you see, here's the portrait, and here is the equation. Now we have a little connection to everyone's personal story. So on another hand, chemistry is science of molecules connecting, assembling, disassembling, breaking, and forming chemical bonds. Molecules are composed of positively charged ions and negatively charged electrons. Electrons are waves, right? I'm not lying yet. But even one electron is complicated. One electron is hydrogen atom. But hydrogen atom, as you will see maybe closer by the end of the course, it is a really challenging problem for solving without a computer, for pen and paper. And it was a challenge for like a century. So the experimental results were available, but no theory. And theorists were competing who will make it better. So although scientifically there is nothing simpler than hydrogen atom, it's still too hard for us. We need to find something simpler than hydrogen atom. Hydrogen atom is composed of what? Proton and electron. Let's get rid of proton and look only on electron. So assume a universe which is empty, like a space with only one electron in space. On one hand, but on another hand, we are already equipped with knowledge in quantum theory. So this electron should obey quantum laws. So let's look what will this poor lone electron, how it will perform in the free space. And free space in our regular universe has 3 dimensions, x, y, and z. So to complicate, let's take only one. So one electron in one free space. This is something where our strengths should be sufficient to solve. Okay? How? Oh, blank screen is the best. Before we came into this class, you already knew that electron is a wave with SPD orbitals. But from another point of view, there is this particle wave duality. So on some sense, the electron can be a particle localized somewhere. Maybe not too much distributed over the whole universe, but in the vicinity of some mathematical point. On one hand. On another hand, we still know that it is a wave and it cannot be absolutely localized in a mathematical point. It will be distributed in the vicinity. So the stuff that we have introduced, or Gauss is introduced, is a good starting point. So assume that we submitted electron to a free space by sending it from electron gun, or by just nailing it down to specific spot. And by its nature, it is a very good assumption and approximation that it will be localized in the vicinity of center of Gaussian distribution and a little bit less probability aside. So our goal is to set the Gaussian shape of electron as initial condition and to look for time-dependent Schrödinger equation to follow up what will be the evolution of this initial condition with time. Okay? You know better than I what is Gaussian distributions since you were grading. So it's exponential to the power of minus independent variable squared. And if it is centered not around 0 but around some point in space, then you subtract independent variable minus center of the distribution. X naught is center. And in the denominator is width, how broad the distribution is. Large width, broader distribution. Small width, narrower distribution. And the width comes into spots in the denominator of power of exponential and in the denominator of the prefactor if we want it to be normalized. So before we start any mathematical exercise, what are your intuitive expectations of this? How the shape of the elephant, how the shape of the wave function will change, if it will change ever? What will happen to wave function if we let it evolve in time according to Schrödinger equation? Super. You can skip 2 weeks. We will be just proving it mathematically. What else? Yes. Right now, if we literally take this initial condition, it will do nothing else. The center will stay at the same point. But if you think of an electron as classical particle, it also has potential to move. And we can, by doing some little tricks to this initial wave function, specifically by doing minus I(x) into here, we will make the whole wave packet to move, and it will be a lot of, I wouldn't say pain, but a lot of exercise to find out that the motion of the center of wave packet will be the same as for a classical particle. So according to whatever one of the 3 Newton's laws, the particle on which doesn't experience any external forces will keep moving with its initial velocity on the straight line with a constant velocity, right? So if we carefully apply Schrödinger equation to this initial condition, we are going, or we expect. Right now it is a hypothesis, right? So we all are growing scientists, and we formulate the little research by posing a question, challenge what will happen to this system this time, and we offer hypothetical answers, which we can prove right or wrong with our instrument or mathematical tools. And hypothetical answers that if there is a non-zero initial velocity or initial momentum, it will move with the center of wave packet. Will move constantly without changing the velocity. And second hypothetical answer that the width of the distribution will change in time. Our hypothesis is that it will increase. Right? We discussed this. So, expectation value of position that we were talking about on your presentations, one of the observables is center of the wave packet, or expectation value of position. It will move wherever it was initially with velocity times time interval. That's good. So it's one of, this is only a hypothesis. We didn't prove it yet. This is a hypothesis originating from our common sense and classical physics, right? And we are going to check whether it will be supported by quantum calculations. Okay, so here is the And do not worry, I intend to finish in time, although we started later. So in order to answer or to prove these hypothetical things right or wrong, we need several checkpoints. So, and we already got some of them. So plane wave, right? So it's just exponential. Momentum operator, minus I h bar ddx. Time independent Schrödinger equation, yes. You can write it down with closed eyes in the middle of the night. Eigenvalues of energies which come from time independent. Eigenfunctions of Hamiltonian. Hamiltonian, we need to put it here. Hamiltonian. We'll discuss it, but it will be easier. If it is a free space, there are no ions, there are no walls, there are no semiconductor quantum dots, there are no enzymes. So in free space, the potential part of the total energy will be zero. So the whole Hamiltonian will be composed only of kinetic energy. And kinetic energy is p squared over 2m, and momentum is this stuff that we defined derivative. Third way to predict future, right? You have it. And then just we practice it further by finding expansion coefficients of this initial condition over eigenstates of this Hamiltonian. Do not feel embarrassed if it looks as a collection of unclear statements. It's only a heads up. We'll go slowly over all of them. So it is a plan to prove right or wrong two hypotheses. Linear motion and expansion of the thickness. So traveling wave is the first concept we discussed when we saw each other for the first time. So it is some function where in argument you have something depending on position, something depending on time, right? And if you make ratio of these two things, it will be velocity. So there is a little ambiguity in definition of plane wave. So in narrow sense, it is only spatial part that depends on position. In broader part, it is spatial part multiplied spatial part multiplied by exponential of the energy of this plane wave. And if you bring it in, then it will be plane wave in a broader sense, traveling wave with a constant velocity, with certain momentum. And if you look, same concepts as we practiced before are applicable. So wavelengths, how dense are fringes in space, and period, how quick it oscillates. Genius 7 years. So thickness may change, either increase or decrease. We already hypothesized that it is increasing. Okay. This is a repetition of what we discussed when we have started our acquaintance with time-independent Schrödinger equation. So time-independent Schrödinger equation is one of the examples of the eigenvalue properties. When operator acts on function, resulting in the same function multiplied by constant. And the first example that we explored was eigenvalue problem of the momentum operator rather than Hamiltonian. Vaguely remember it. So if we act with, so here's momentum operator, here is the plane wave in narrow sense, plane wave function. So this is a repetition of what we did before. So if we apply momentum operator to plane wave function, we practice this derivative, and derivative doesn't change functional form of the exponential. So it remains exponential, but as a price of this derivative, the value of momentum comes up front, right? And then you will see that by acting on with momentum operator on the plane wave function, one is getting momentum value multiplied on the same wave function, because everything else can be cancelled, right? So plane wave function is an eigenstate of momentum operator. Plane wave is eigenfunction of momentum operator. I'm just lazy. What is Hamiltonian with this free space? 1 over n, 2n p squared. We are not in math class. We're not going to prove stuff. But it looks natural, and it can be proved that if a function is an eigenfunction of certain operator, it will be also an eigenfunction of any power of this operator. So any function that was eigenfunction of momentum will be also eigenfunction of momentum squared, momentum cubed, momentum fourth power. So very lucky for us. We do not need to diagonalize this Hamiltonian. And under word diagonalize, we assume the finding eigen values. I remember in previous class there was a little discontinuity between these two terms. So finding eigenvalues and diagonalize are equivalent terms. So if we act by this Hamiltonian onto wave function which is plane wave, we will get some eigenvalue times the same plane wave. Right now it is a hypothesis, but it is very natural, and we can check it. So after we do everything, we will get an expected answer. So we will be looking not on the wave function as a final answer, but wave function squared, because what can be interpreted as you guys presented, right? So the interpretation belongs to wave function squared, and it is expected to be some prefactors, some Gaussian where the central part may move with momentum, and the denominator is expected to expand to be what it was at initial time, and then additional, so it will expand quadratically. Do you have anything else? Okay, I think it is the last slide. We will go to details on Friday. So practically, if we want to apply a third way of predicting future, we do need to find expansion coefficients that will enter into our future. So we need to take our past, which is a Gaussian wave function, multiply it with eigenstates of Hamiltonian, take integration, and get the expansion coefficient. So the mathematical task that we will be practicing when we meet on Friday will be taking Gaussian taking plane wave and integrating their product. This is possible. This is doable. So a little effort, but it's adequate for like, third year undergraduate. And And if you're a fourth year, you may know the answer right away. And you can find the answer in the Wikipedia or whatever. The homework that I suggest you bring, next homework number 2 that I suggest you bring on Monday, is essentially practicing similar thing. So Fourier transform is Fourier transform of a function is taking function, multiplying it by oscillating exponential, and taking integral. And it is very standard problem. I think I'm out of time, which is solved very frequently in engineering, in electrical signal processing, and in making your sound nice for your headphones. Thank you for the questions and dedication to the course. Meeting is done. Looking forward to see you today at 5 downstairs. If the equipment will not perform as we wish, we have a backup class in lab hall in chemistry, where everything works for guarantee, but they do not have recording facility.